The session's on disorder. We're going to be talking about we're going to focus on a particular methodology that we've developed here at Duke for modeling disordered systems. But yeah, this is going to be a big departure from the modules that we've looked at earlier, which have all made a big assumption of periodicity and assuming that we have a crystal system. So what is disorder? Okay, so if you remember from my first talk, we made this assumption, which was very much necessary because we needed to reduce the number of equations and the number of variables we needed to solve. Here we have a zinc oxide crystal system, which is the idea of periodicity is what we've been focused on for the week. And because we have a periodic system, we can reduce down this macroscopic material, something that we can see with our eyes, down to a repeating unit cell. Okay. And this of course assumes that we have order, we have symmetry, we have periodicity, all of the above. This is an ideal approximation. The real world has impurities, defects, randomness, and disorder. So this is purely an approximation, and really when we deal even with crystals, there's going to be some amount of disorder and some defect in it. There's a lot of different types of defects and disorder. I'm going to focus. Well, we're going to talk. I'll mention two, and we're going to focus on one. Here we have structural disorder, which is prevalent in glass. Okay, so we have here we have a crystalline zinc oxide system, and you can see that there's a repeating unit. The atoms are situated in a particular position in space, and that's repeated in all three directions. That structural disorder does not exist in glass. It looks more like a liquid in the sense that the atoms sit in random positions. We can also have chemical disorder. Okay, so we retain the structural disorder, the structural order of a crystal, but the sites themselves can be occupied with more than one occupant. Okay, and the way we characterize this is with probability. So we have a zinc site here, which is fully occupied. So this has no disorder on that site, but this site here, the magenta and yellow site here, this has some chemical disorder. It's randomly occupied with sulfur and selenium. 25% of the time it's sulfur, 75% of the time it's selenium. Okay. So I want to make that distinction between structural and chemical disorder. Okay, so this was a picture I showed in my lecture on thermodynamics in the A-flow convex hull module. I said it would come up again. I want to motivate why disorder is so important. So here we have the enthalpy of formation for across a compositional space of palladium and platinum here. We have the pure components up here, and we have the mixture at the bottom. And I told you that this was the enthalpy of formation. Another way of looking at this is called the enthalpy gained from going from pure component systems that only have one component respectively to two components. Okay, so there's an energy release there, right? Because this is lower in energy. We can generalize this analysis, and I showed you the plot yesterday of what we can do this for all metal systems in the A-flow database. We can also do it adding an additional component, and so we can look at the energy gained from going from one or two species to now three species, and we can keep going. So this is another visualization or another plot of the data I showed you yesterday, where I showed you that the enthalpy gain decreases with dimensionality. This plot shows that pretty clearly. So we can go from, we have, I showed you the 2 dimensions, the 3 dimensions, and 4. The first dimension here, you can think of it, this is the cohesive energy. So this is from going from atoms existing in space unbonded to now a crystal system. That's the cohesive energy. So you can see here that the energy drops off very quickly with the number of species. Okay, this is on average. So you can see we go from EV per atom to now millielectron volts, hundreds of millielectron volts, down to very small amount. And remember that not only is the energy decreasing with dimensionality, but the number of compounds that show any increase at all decreases, right? So we might have a ternary that's up here, in which case it shows no gain with respect to the binaries and unaries. So it drops off very quickly. We can compare this n+1 enthalpy gain with the entropy gained we get from increasing the species. Okay, so this is just assuming ideal entropy. This is the equation Boltzmann derives. So we have the Boltzmann constant times temperature times the logarithm of the number of species here. Okay, this is just ideal entropy. So we can look at this. We can look at it as the system, whether the system's completely disordered, so all the sites are randomly occupied, or we can isolate the randomness, as I showed you on the previous slide, to particular sites, which we can identify as sublattices. This concept I'll make a little more clear in the upcoming slides. But even as we sort of decrease where or isolate where the disorder is, you can see that fundamentally entropy is going to overtake the enthalpy. And so what does this mean? What's this conclusion mean? This conclusion means that as we continue to look for more multi-component systems where we can get sort of, you can think of them as getting a blend or a mixture of different properties or additional properties, we can expect that disorder is gonna be a big part of the equation there. So we cannot ignore disorder, as we've done in the workshop, in the lectures we talked about previously. We really need to incorporate disorder. It needs to be part of the analysis, and it's going to be a big piece of characterizing these materials. So how do we model these types of materials? You know, we cannot just go to our VASP input. We can't tell the postcard, for instance, that we have random occupation. That's not really available through VASP. So there's a few approaches in the field. Broadly speaking, there's mean field approaches, and then there's a supercell approach. Mean field approaches include coherent potential approximation, virtual crystal approximation. These mean field approaches, in general, they're single site approximations, and so that means that we're not going to be incorporating local distortions. And what I mean to say is that you can imagine that if I had a sulfur atom, which was if I had a site where there's sulfur and there's selenium, you can think of this way. The two of them are going to be different in sizes. They're going to have different electronic character. And so there's going to be some warping of the lattice. Being that these mean field approaches are single site approximations, it's not going to incorporate these local lattice distortions. You can think of it as, roughly speaking, that if we have blue atoms and red atoms that are sitting on the same site, that we're going to somehow model it as a purple atom, where we take the average of the properties and we model it as a single site here. So virtual crystal approximation is similar. One caveat is that the components have to be very similar electronically, otherwise the approximation is not very good. Another approach, which is very popular in the community, is called the special quasi-random structure approach. Okay, so we effectively model our disorder as a supercell, or disordered system as a supercell. I'm going to talk more about this in the upcoming slides, but the idea here is that, in general, for these special quasi-random structures to be valid and for the model to work well, we need very large cells. These cells are going to be very low in symmetry, and there's an implicit assumption made that we're choosing our representative structures is the one that's chosen is the one that is the most random. Okay, and so this is what we call the infinite temperature approximation, and we may not be at infinite temperature. Okay, so this implicit assumption is very important. Okay, so we have a new approach. It's called AFLOPOC for partial occupation, and the idea is very simple. So we have a magnesium oxide crystal here. You can imagine that if we had X-ray vision and we can analyze the structure with our eyes without looking at without using X-ray analysis, that we might see a structure like this. Doesn't matter where we look in the crystal. The fact that it's periodic means that it's going to be the same repeating unit everywhere in space. If we dope our system with a bit of zinc, then we might look at a particular piece of this crystal and we might see the same structure But as we look around, we'll see that the sites that were uniquely occupied with magnesium are now also occupied with zinc, depending on where we look. Okay, so that's the idea that I want you to keep in mind. We're going to be modeling our system as an ensemble average of the different supercells that can exist everywhere in space. Okay, so how do we do this? Well, here let's go back to our original example. We have our zinc, sulfur, selenium system here, where we have a site that's randomly occupied between sulfur and selenium. If we take this cell and we make a supercell of size 4, you can see how we can represent the stoichiometry exactly, because now we have 4 sites where we used to have 1, and in which case we can have sulfur sitting at one site and the other 3 sites are occupied by selenium. Okay, and the idea here is that there's going to be a bunch of different ways that we can make supercells that have that constraint satisfied. Okay, so let's be more specific here. So we have our primitive cell, and if we make a supercell size of 4, as I said earlier, we can have one site that is sulfur and the other 3 sites is selenium, and you'll see that this cell satisfies the stoichiometry of the system we had earlier. Okay, but the idea here is that this is not the only arrangement that's allowed. We can take the yellow atom here and we can put it in all the other positions. Okay, so we get at least 4 different permutations on the different ways that we can arrange the atoms, and all these supercells are representative of the structure we had earlier. Okay, now it turns out that because of the space group that we're working with, because of the particular lattice and the arrangement of the atoms, all of these are equivalent. Okay, so if we plug these systems in individually into VASP, we'll find that we get the same energies at the end. Okay, so they're equivalent. So the way I created a supercell size of 4 earlier. There's different ways of making that supercell size of actually. So I showed you a way of that we have sort of degeneracies with the sites inside of a particular box, okay, of a particular unit cell, but the way we make the shape of the box is also not unique. So the one I showed you earlier was this one. Okay, so we basically expand the cell equivalently in all directions, but we can also do an expansion in one direction or in a diagonal direction. Okay, and so the shape of the box is also not unique, and so we can actually figure out all the unique ways of making different supercell shapes. Each one of these will have its own permutations of the sites too inside. Okay, so it turns out that for this system, there are 7 different cell shapes that we can make, and each one of them has 4. So there's 28 different supercells that we can make for this system. Okay, and a very important idea here is that the algorithm we're going to be discussing today, it considers all of these decorations. There are some algorithms in the community which only focus on this supercell, okay, and they don't consider the other structures when we're doing our averaging in terms of averaging the properties of the system to get our disordered system. They only consider one type of cell. Okay, and so the algorithm we use considers all of them. Okay, so here we have our okay, so the basic idea is that we want to take all of these structures, and they're gonna be we're basically going to average our properties across all of the different supercells that we can enumerate. But I didn't tell you how we're going to be averaging them. So there's going to be a weighting associated to each supercell. Okay, and so if we look at, we had 28 total structures. It turns out that only 7 of them are unique. Okay, and so among these 7 unique structures, we have a degeneracy associated with each of them, and it turns out that each one of them carries a degeneracy of 4. So there are 4 structures that are equivalent to this supercell, 4 structures that are equivalent to this one. Okay, so keep that number in mind. We can plug these structures in. These structures are crystalline. Okay, so they're periodic. We can plug these structures into VASP, calculate their energies, and or their enthalpies, and get a value for each 7 of these structures. One of these structures is going to be the ground state. Okay, it's going to be the minimum energy structure of the 7. Okay, so we're going to denote that the ground state. We're going to derive the properties for each one of these 7 structures, the probabilities, based on a Boltzmann weighting. Okay, so let's talk about what goes into this Boltzmann weighting. Okay, so we have the degeneracy, as I talked about. We have this exponential term, which characterizes Boltzmann probabilities. We have the difference of the energy of each individual structure from the ground state. Okay. And then we divide it by the Boltzmann constant and then a tuning parameter, which is loosely correlated with temperature. And so this temperature parameter, we can vary the temperature, and temperature is going to tell us how much disorder we want to incorporate in the system. Okay, so if temperature is very low, then that means that the probabilities of all these structures are going to be close to 0, except for the ground state, okay, which is going to be 1. And so the system, the disordered system, is going to be heavily skewed to the properties of the ground state. The alternative is if we turn up the temperature, then all of the probabilities of the structures are, well, all of these terms, the exponential terms, are going to be equivalent. And then the probabilities is going to be skewed by the degeneracies, which in this case, it's all equal. So in this case, the probabilities are all going to be the same. Okay, so they're all equal probable in our picture of looking at the crystal. We expect to see all 7 of these configurations appear in equal probability. Okay, so a question I get is, what is the difference between POC and SQS? SQS being the special quasi-random structure. I think it's important that we talk about what is SQS and how we derive it. SQS is really an application of the Ising model. Okay, which the Ising model, for those of you that don't remember or didn't study it in physics class, the Ising model was developed to understand the magnetic transitions, in particular ferromagnetic ordering to paramagnetic ordering, where we don't have a magnetic moment in the material. Okay, so what happens here? So we have a system where the energy of the system is dependent on what the spins look like as neighbors. Okay, so we can have a system of spins, and you want to look at the neighboring spins. And so we can either have a ferromagnetic system where it prefers to have all of the spins aligned, or you can have a system where it's anti-ferromagnetic, where the spins prefer to be anti-aligned. So the idea here is that this ordering of the system having the spins all aligned, this is going to be broken by temperature. Okay, so we have our system here of all spins up as our initial configuration. And as we incorporate temperature, temperature is going to induce this tendency for spins to flip. And more spins will flip as you increase the temperature. And at some point you approach a phase transition where more often, where basically half of the spins randomly are going to be spin down and half of them are going to be spin up. And it happens at a very sharp transition. Okay. So the idea here is that we want to look at the correlations of the spins locally. So let's look at the pictures of the 2 different low temperature versus high temperature. At low temperature, we have all of the spins aligned. There's a tendency for these spins to be aligned. This picture is very different than the disordered picture, where any given spin could be up or down. It's random. This idea is what SQS is about. So replacing the concept of the magenta versus the yellow atoms, we take the magenta atoms to be spin up, yellow atoms to be spin down, and we want to analyze the correlations in the unit cell. Okay, so what we do here is we quantify sort of the average correlations in the system. Okay, so we look at we look not only at pairs of spins that are nearby each other, but we also look at triplets, and we can look at spins that are next nearest neighbors, etc. So we assume all of these things in this average correlation function. The exact formula is not that important, but just get the idea in your head. One of these 7 structures is going to have the lowest correlations, the lowest average correlations, where spin up is really is next. The next nearest neighbor could be spin up or it could be spin down. The idea here, though, that the concept that's very important here. So we make a choice here of one of these structures is going to be a representative structure. So of all the 28, we're just going to pick one cell to represent our structure. The problem here is that while I said one of them is going to be the minimum, I didn't tell you how close to zero that number really is. And so in order to get the correlations to match that of the random structure, we really need to get a very big cell. Okay. And in practice, we see supercell sizes of 80, 100, 150. And really by choosing one supercell, that which has the lowest correlations, we're implicitly assuming that we want one cell that has the lowest correlation. So we're assuming ideal disorder. And this only happens at infinite temperature. Okay. Whereas we expect that our system, you know, the systems we work with, the materials we work with, we're not working with infinite temperatures. Okay. So that idea of whether we're at the infinite temperature extreme or regime, that's a big question. Okay. So POC and SQS, they're sort of counterparts in the sense that they achieve disorder in different ways, but they both do indeed achieve modeling disorder. SQS does it by modeling it with bigger and bigger and bigger supercells. They do it with one supercell that gets bigger and bigger and bigger. Okay, so we model it with one big supercell. POC, on the other hand, does it by modeling it with smaller supercells. They do get larger, but the idea here is that there's more of them. Okay, and so we model it more toward the other end where we model with more cells versus getting larger. And so we have an ensemble. Okay. And so therefore we get away from this infinite temperature solution or approximation, this assumption. SQS, being that it is infinite temperature, it's not going to model these phase transitions unless, of course, the phase transition happens at infinite temperature. And so it's this transition from precursors to the mixed solution that's not going to be well modeled by SQS necessarily. We really need a basis to model it. And so POC is really, you can think of POC as being a superset of SQS. POC brings an additional practical advantage in the fact that we're modeling we have to put these systems and we have to run them on our machines. And it's always much easier to run many smaller calculations than it is one giant system. Because to model one giant system and to parallelize that across different nodes and in different racks, different systems, that's gonna slow down that calculation. And so if we can run independent systems parallel, that's going to be a much faster calculation. Okay, so we're going to get to our practical part of our example. I'm going to stop sharing and I'm going to share my full screen. Okay. So let's open up our browser and let's go to aflow.org. And let's go to aflow online. Everybody can see my screen here with the browser, right? Just give me a thumbs up if you can. I actually can't see. Yep, perfect. Okay, great. So, all right, we're going to click here, input part car. Okay, so we've created it, we've extrapolated from the postcar structure to create a part car, which is the POC equivalent for the postcar. So let's talk about what we have here. Okay, we have a system where we have carbon on one site and we have a metal site which is randomly disordered between hafnium and niobium. Okay, 50-50. Okay, so how is this structure different than the postcar? We have our scaling factor here. It's negative because in VASP, I don't think we talked about this. I don't remember, but we have a scaling factor. Usually it's 1. We've been treating it as 1, but if the number is negative, we treat that as the volume of the system. Okay. This is understood by VASP, no problem. These two numbers here is a little different. This is not in the postcar. These numbers are the tolerances we need for modeling our system. Okay. So we're gonna treat these as we want to model the system exactly. So we want to find the supercells that model the stoichiometry exactly, but these two tolerances, we can play with them, and we can actually introduce some error in this in the stoichiometry and in the site, in the site, in the occupancy of the site uniquely, to create structures which might model the system, which might have some error in terms of how we model the system, but it's going to reduce our calculation, or the amount of resources we need to give to model the system. We have our lattice parameters here, no problem. This is the same as the postcard. Here we used to have, if you look at the postcard, we used to have integers here. Now we have fractional coordinates. We have, excuse me, not fractional coordinates. We have fractional occupancies. So we have 1 times 1, meaning that our carbon site here is uniquely occupied. And then we have the next 2 sites, which are occupied 50% each, okay? We have our site here, which is at the origin of carbon. And then we have we have two equivalent, these two sites are equivalent. Okay, you see they sit at the exact same site, but one of them is hafnium and one of them is niobium, and they're 50-50, okay? So that's the part car. If you have any questions, put them on the chat or let me know, but that should be pretty clear. But we're actually going to run a calculation on this input. If you scroll down to partial occupation, let's click on optimize HNF value, and then we're going to hit submit, and it's going to scroll down for you, and we're going to get some output. Okay, so let's see what we get here. We get some verbosity from the algorithm telling us that we have, this is the system it read in and understood. Okay, so this matches what we had above. It's going to show you, it's going to do some cleaning, and it's going to change the representation of the structure. It's actually going to give you what the parent structure looks like. So if we remove all of the disorder from the sites, it's actually going to show you what structure exists underneath. Okay, so it understands this is actually a rock salt structure. Okay, this is the FCC lattice with a basis of 2. So this is the rock salt structure. So it's able to derive that. We're going to skip this part here. This is not too important for understanding. This is important for the algorithm, but it's basically giving us some verbosity. And now we're getting a table showing us how it's going to find what is the best representative supercell size for our system. So it's going to first try to model the system with a supercell size of 1. And you're going to see that with a supercell size of 1, it's going to have a relative error of 0.5 because it can only make a choice of either I occupy that one site with hafnium or with niobium. And that's going to give us an error of 0.5 on that site. And the stoichiometry is going to be an error of 0.5 as well. We're going to have carbon hafnium or carbon niobium. Now it's going to increase the supercell size to 2. And if we do that, now we can actually model our system, our stoichiometry exactly, because now we can place at one site niobium and at the other site hafnium. So now we have no error. The algorithm recognizes that this is a viable choice. And so the optimized HNF, which stands for Hermite normal form, which is just a supercell size, value is 2. Okay. Unless there's any questions, we're gonna scroll back up, and I'm gonna click on calculate Pox supercells. So not only is it gonna find the supercell size, but it's actually gonna give you the representative structures that we're gonna use to model our disordered system. So we're gonna click on that, hit submit, give it a second. We're gonna have some of the same output as earlier. We get the table again. We get that same table. We get an HNF value of 2. And then it's going to check how many different ways can I swap the niobium and hafnium. Well, there's only 2 ways. I can swap them once, and then I get 2 different permutations there. Okay, so that's the site permutation. So between the number of HNF matrices and the number of permutations of the site, I get a total number of supercells of 4. And the algorithm is going to approximate what the unique, or it's going to try to figure out what the unique supercells are of these 4. The way it does it is called the UFF energy approximation. So it's kind of a mean field approach. It's basically going to assume energy values for each of the atoms that we have in the cell, and then what atoms are bonded. It's going to make some approximations there, and it's going to add up all of these pieces to give you an approximate energy to the structure. Using this approximate energies, it's going to check which ones have very close energies, and it's going to label those as not being unique, as being degenerate. So the algorithm found that there are two degenerate structures, and so there's going to be two unique structures. Okay, and then it gives you those structures here. These are perfectly ordered structures. You can take these, plug them into VASP, and derive and calculate their properties. Okay, and we know that they have a degeneracy of 2. Okay, so are there any questions so far? I think I covered everything I wanted to cover. Okay, so now we're going to do an exercise. We're going to do this together. We're not going to go into the breakout rooms. And we're going to, so I'm going to ask that you scroll back up, and I want you to create the part car. So I want you to modify this input here. You can actually type here. So you can go ahead and type. I want you to modify this input structure to create a 5-metal carbide. So we have a 2-metal carbide here. I want you to make a 5-metal carbide having molybdenum, niobium, tantalum, vanadium, and tungsten. They're going to be equally probable. Okay, so instead of having a partial occupancy of 0.5, they're going to be 0.2. So I want you to create that part car, and then I want you to find out how many derivative structures there are. So one note is that they have to be alphabetic. So you have to have molybdenum first, then niobium, then tantalum, then vanadium, and then tungsten. Okay, so I'm going to give you a few minutes. We'll wait till 3:40. And if someone gets the answer, they can post it on the chat, or they can unmute themselves, and they can tell me what I have to change in the part card to make it a 5-metal carbide. Recording. Go ahead.
So looking at the part car line 6 with all of the multiplication signs, we've got the 1 times 1, and then it started off with a 1 times 0.5. There were 2 of those. We're going to change the 0.5s to be 0.2, and then we're going to add some more onto the end until we have a total of the 5 of those 1 times 0.2 terms. So we'll have 1 times 1 space, 1 times 0.2 space, etc. And we'll have a total of 6 terms there. 5 of them will be this 1 times 0.2. Then underneath, we're going to take our, just copy one of these lines that had the niobium on it, and paste an extra 3 lines of that to the bottom. So we should have the total of the carbon on the origin, and then a bunch of lines throughout the rest that say, like, a bunch of niobiums at 0.5, 0.5, 0.5. We'll go ahead and change the metals from being hafnium and niobium to being from top down in the molybdenum, niobium, tantalum, vanadium, and tungsten. And we'll make sure they all have the POC of 0.2.
Perfect. Excellent job. So that's great. Just in case anyone was wondering, this line, so from VASP, the only thing that matters from this line is the capital D. We either have capital D or capital C. So the 3 here, we don't need to change that. I mean, you can change it to be better. You can change it to be 6 if you want. And actually, AFL does require the P here for partial. And then if you want, this is also just another comment, but we can also change this to 0.2, and etc. We don't have to. It's not necessary. The reader doesn't understand, is not going to read that part. But anyway, so we're going to scroll down. We're going to calculate the POX supercells, and we're going to hit submit. And it looks like you guys got the answers already. So I'm not too, I don't remember how long it takes, but it should be pretty fast. But yeah, you'll see here that the algorithm finds 49 unique supercells. I really want to emphasize that this is unique to the fact that we're using the UFF parameters and the UFF energy. If you took David's comparison algorithm and you ran it, you'd actually get you would get a different number. So we avoid, because this algorithm is very fast. It's very fast to calculate the UFF energy. I think it's orders of magnitude faster. To do the symmetry analysis and to figure out structurally which structures are unique is a much slower process, but it can be done with A-flow. So, but to do this quickly and to do this for, in a high throughput sense, 49 is actually enough. This is a good sampling. Okay. So I'm going to continue with the slides. Let me just check. Yeah. Okay. So I'm going to show you a bunch of command line options. And then we're going to definitely break up into breakout rooms, and we're going to spend quite a bit of time in there working through some of the examples I give you for creating the different POC structures, how you can create it with the command line. All of this has been automated, and there's we've created a very nice scheme for how to create these structures just from a basic input line in the terminal. And then we'll spend some time practicing on that. So let's pick it up from here. Okay, so, all right, so how do we create a POC structure? Okay, so I always recommend first and foremost to create the parent structure first. Okay, so our parent structure has always been rock salts. This is kind of our favorite here. So we have our designation as per the A-flow prototype encyclopedia designation, right? We have the composition here, the Pearson symbol, space group, and then the Wyckoff positions. And then parameters, the only parameter here is the volume, and so we automate the volume with regards law. So here we've created our parent structure. Okay, I want to point out some key ideas about this structure. So this structure has a basis of 2. So there are 2 species. Okay, so there's not only 2 sites, but there's also 2 species. We have A and B. And then we have 2 site positions. Okay, so I'm going to emphasize the S here and the P here. Okay, so we have 2 positions, but we also have 2 species. We could have, for instance, 3 species and 3 positions. We could also have 2 species. We could have one species and 2 positions, right? This could be A and A. Okay, so I hope that distinction is clear between the number of species and the number of positions. Questions now. Okay, so we're going to create, now that we've created our parent structure, we can add on to this parent structure a command to create a POC structure. Okay, so let's walk through these, what I've done to what I've changed to the command to create this POC structure. So what I've done is, if you remember, if you put colons, you can actually specify the species here. We're going to have 5 species, and they need to be in alphabetic order, right? Carbon, molybdenum, niobium, tantalum, vanadium, tungsten. That's the structure. That's the one I had you do in the exercise. And then we're going to add on the POC parameters. Okay, so we had parameters from before, and then we're going to add POC parameters. Okay, so let's be very careful here because this is tricky. So I'm going to specify that I want to have position 0 fully occupied with the carbon. Okay. So position 0, that's the first position. So we start with 0, dash 1 times A, where A corresponds to the first element I give in this list. Then I have an underscore, and I say position 1, which is now the second position, right? Because we started with 0, dash 0.2 times B, so 0.2 times molybdenum, 0.2 times niobium, 0.2 times tantalum, so on and so forth. Okay, so that's position 1 is partially occupied with all these metals. Okay. That's going to create, if you run this command on the command line, you're going to get this part car printed out to your screen. Okay. And it's exactly as Josiah specified earlier. We have our default tolerances here. We have our partial occupancy numbers here, and then we have our sites, our partially occupied sites here at the bottom. Okay, just as we talked about earlier. Okay, so we can take this part car, pass it through AFlow again to get the HNF value, and then the number of supercells, right? Just running those two commands that we ran from the website. So we take that input we had, and we add a pipe to pass it into AFlow again, and we run it with minus HNF. We're going to get the output that we saw on the website. And it's going to follow up with the table. Okay, this table that we saw, but the table's going to, we were running it for a 2 metal carbide. Now for 5 metal carbide, it's going to have a few more lines because it has to get to a supercell size of 5 to realize 0 error in both the sites and the stoichiometry. And we get an optimized HNF of 5. If instead of minus HNF, we run minus HNF cell, now we're going to get the number of unique, we're going to get it's going to print out all of the unique structures. Okay, and so you're going to get 49 of these ordered representative structures. Okay, if instead of proto, we run AFlow proto, it's going to create an AFlow in with with additional parameters where we have AFlow POC, where we have this calc input here, and then it's going to print out the part car here. I'm going to run this example actually. Let's run this example together. So let me share my full screen. Stop sharing. I'm going to share my full screen. Okay, so let's go to the terminal. Module load. AFlow. I'm going to go into day, what are we, day 4?
Right, there's a question in the chat, but I think you're answering it. You're answering it right now.
Okay, great.
Is there a way to compute the POC supercells from the command line? I think that's
yes, perfect. Absolutely, I didn't see that. Good thing I didn't even read the question, but it's there. Okay, let's go inside of 12 POC. Let's go inside of exercises, and let's go into Scratch. Okay, so just to demonstrate, because I didn't do it earlier, I'm going to run this proto command. So I'm just going to copy it. You should be able to copy it from the PDF. And I'm going to, remember we have to do this paste thing here. So I'm going to paste it into the terminal. It's kind of long, so we don't want to write it all out. Enter. And you see that it prints out the part car. Okay. And if I pass this command to minus HNF, I actually get in the output, I'm going to get that AFlow calculates an optimized HNF of 5. And then if I go up and I do HNF cell instead of HNF, then it's going to run the full analysis. You see it takes a little bit, and then I get all 49 structures here. So this is all from the command line. Now, instead of the proto command, we want to do this high throughput. So I'm going to create an AFlow in. Copy that. And I'm going to paste the command. It's important to remember that we have the generate AFlow in only parameter there. So that's why I recommend copying and pasting. So now it created a new directory here, AFlow data. We're going to go inside. Okay, let's look at the structure. So we have AFlow data, and then the structure has the species. This is, think of it, so that the directories are created with a particular structure. So the first layer is the chemistry layer or the pseudopotential layer. So here we have all of the pseudopotentials labeled here. Okay, so we have carbon, molybdenum, PV. This is the particular pseudopotential we choose. niobium, SV, et cetera, and it's calculated with Paul PBE exchange correlation functional. So let's go inside the next layer. And now we have, it's in green. But if okay, so you can't see it all that well on my screen. Let me zoom in too, so maybe you can see it a little better. Can't see with the color because it's a directory. Let me just change it to 755. Okay. So the first, now we have the structural layer. Okay, so we had originally, this is our backbone parent structure, the rock salt designation. And then we have this POC. The POC params becomes part of that string to create the directory. So you see this is unique to our input. Okay, so we're going to go inside there. And now we're going to open up the AFlowin. I'm going to do it with gedit. And I'm going to zoom in. Oh. Okay, this should be more legible. So I'm going to go to the bottom. So the bottom is really the more important part. So the piece that's different here from the other AFlowins we played with is that we have this AFlow POC tag, which tells it to run an AFlow POC calculation. And then we have a part car where we used to have a post car. Okay. So it says POC mode, it's explicit, stop and start. And then we have our part car there. Okay. So let's go ahead and close this. Close without saving. We can actually run this. So we do AFlow -- run. Just like before. And it's going to create. Okay, so right now it's actually writing out. It's going to write out a very large file. So it may take a few seconds. But basically it's going to create A runs for all 49 structures. You run all those A runs in parallel. You can run them on a cluster, run them in parallel. And then the idea here is that once they've all been run, you run AFlow run again in that parent directory, and it's going to go in and analyze all 49 A runs and give you back the ensemble average properties. Give it a second. It's actually trying to write out all 600 structures to a file in case you need it. You don't need it. There are 600 structures, 49 of which are unique. Okay, so if you write ls, you'll see that all 49 structures appear here. And now these structures, the influence of these structures can be run with VASP, no problem. They contain, I'll just show you with VI. I'm just going to do this on my screen here. You don't have to do it with me, but this is a normal AFlowin with a postcard that could be run with VASP. Okay. All right. What I want to do now, I'm going to come out of this. All right. I want to really drive home the concept between P and S, positions versus species. Why is the S so useful? Imagine that we were dealing with a different prototype. Instead of rock salt, we had this prototype here. Okay, so if I click on this and I open it up. Cementite. Okay, so cementite has a very large basis. So I get the output here. So imagine that we use this cementite as our backbone. So you see we have 4 carbons and 12 irons. Okay, so we have 2 species and 16 positions. Now, if I wanted to create the POC parameter for this given position 1, position 2, position blah, 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 up to 16, you can imagine that this is going to be an enormous command. Okay. So a shortcut we use instead is we use the S instead of the P. So let's go to our, because we have 2 species. So if I wanted to uniquely, if I wanted to occupy, so I want to keep the carbons all uniquely occupied, and then I wanted to occupy the metals on the iron site here. the way to do this is to specify by doing it with the species parameter here. So let's grab this. We're going to copy it. Paste. Enter. And you're going to see that we're going to create a very big structure. Okay, so now we have the 5 metals. So we have for every iron site, it's going to be partially occupied between all 5 metals. So now we get 64 atoms instead of the, I guess, 16 that we had before. Okay, so species is the key here because we can specify here that we want the first species, which was carbon, to be unique, the sites of all the carbon to be uniquely occupied, and then all the sites of the second species, which is iron, to be partially occupied. Any questions there about how the distinction? I hope that that's pretty clear. It's really just a way of saving energies in typing on the keyboard. Okay, so there's some other high throughput commands that we can run. So there are, okay, so the molybdenum, niobium, tantalum, all of these metals that I chose, these are refractory metals. Okay, they were used in a particular study of carbides that we had that I'll go over some of the results of that in a few slides, but we basically made a choice of, we had a set of 8 refractory metals, and we wanted to make all of the POC combinations of 5 metal carbides. So if you have 8 metals to choose from and you have 5 sites to fill them, there are 56 different combinations. You can actually make all 56 combinations with one command, and the command is provided here. So let me show you what's going on here, because there's a lot in one command, but it becomes very powerful. Okay, so what do I have? I have carbon. So the difference here is I have, okay, so it's going to create it. It ran enter. Okay, so I have carbon as the first site, and that's going to be uniquely occupied. Then on the second site of elements, I'm going to notice that I separate sites here by the colon. So in the second site, I can have hafnium, molybdenum, niobium, tantalum, titanium, vanadium, tungsten, and zirconium. On the third site, I can have the same. On the fourth site, I'm going to have the same, and on the fifth site, and then on the sixth site, all the same. So it's going to make a choice between. So it's basically going to iterate by choosing carbon, hafnium, 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 hafnium. That's not going to be a choice that we want. It's going to do hafnium, molybdenum, then niobium, then tantalum, and then titanium. So it's going to go through all of these combinations where it chooses one of here, one of here, one of here, one of here, and one of here. And so it's going to make, so this was running in the background. You'll see that it went through all possible choices, even ones where you had carbon and zirconium, 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 which is not a choice we wanted. So if you go inside, you'll see that it made all 56 combinations. Okay. One of them has all of the A runs inside. So hold on, let me which one was it? It's this one. Just give me 1 second, because I'm going to. I just want to show you that we have 56 combinations. I'm going to just clean this out so we don't have the. Okay. And then if I do find, if I look for all the different, you'll see that we have 56 compounds. Okay. So that's one way of, okay, we still have half an hour. That's one way of doing the different combinations. You can also have different POC parameters. Okay, so you can have you can do it where, okay, so this one has, this is a choice of this is a 2 metal carbonitrate. Okay, So there's two metals and then there's carbon and nitrogen. And I can specify the POC parameter. I can do one where I choose for the one site to be fully occupied with carbon and the other one to be partially occupied between the two metals. And then another one where I have a 50-50 mixture of carbon and nitrogen on one site and a 50-50 mixture of hafnium and zirconium on the other site. So you can see here, I just separated with a comma. So if I run this command, I get now these two directories. You see here that the POC parameters are here. So if I'll just let me do this. You don't have to follow on your screen, but I'm just going to show you what's inside of the AFO in there. So you see the one has just carbon, and then it's partially occupied. It has a partially occupied site between hafnium and zirconium. And then the other POC parameter that we were able to create with one command, it's like this. Oops. Oh, I didn't copy it correctly. Okay, so this has carbon and nitrogen sharing a site, and then hafnium and zirconium. Notice how these are still in alphabetic order, despite the fact that the two that are sharing sites are not near each other. Okay. So it has to be in alphabetic order. Okay. We're going to spend the rest of the time. We have half an hour, and I expect it's going to take a bit of time to go through all these examples. So we're going to spend the next half an hour doing these exercises. And then I don't think we're going to have enough time. We'll go into break. We'll come back and then we'll talk for a second. We'll go into break. And then when we come back, I'll discuss the solutions. All right. So let's, we got some questions though. If we have O instead of C, how to do the combinations? You just replace, okay. So you bring up a good point, because the fact that carbon is alphabetically before all the others makes it easier to create the commands. This is part of the challenge that I want you to explore in the exercises. So we're going to go into so it's a good question, but I think you can answer it if you think about it a little bit, but it's a good question. So this is something I do want you to tackle, because the next example is with oxides. So it's a good question. So yeah, so I'll have you guys go, unless there's any other questions, we'll break up into our I'll stop recording. Okay, welcome back everybody. So when we last left off, we were doing these exercises. I was wondering if anyone would volunteer to do the first one if they got it. Does anyone have the answer for the first one? Anybody? It's not that difficult. We just have to make a part car. I know some of you got it. We were oh, look, we got a submission. Okay. Very good. Okay, so let's copy this. Yes, I know. Thank you for submitting your answer. Okay, so let's see. Okay, so all right, so let's see what was submitted. So here we have okay, we have the prototype for rock salt. That's fine. We could use this prototype here. This is fine. Alternatively, we could have also used the prototype label I provided. So there's some aliases in AFlow. One of them being this one. So we could also use 201 here. We don't need params for this one. But it looks like, okay, so the first thing is that these species are all together. So let me, okay, let's see if it creates it first. Okay. 0.25, 750. Okay, perfect. Okay, so first, the way to make this, I always stress, first you should make the parent structure to see what it looks like. So proto equals 201. So I give you the prototype. So you get the rock salt prototype here for a generic species. Then we're gonna fill it up. You see that we have 2 sites and 2 species. So we're gonna fill it up with an alphabetic order. MG O C N. And then we're gonna add our POC params equals. And we have we want O to be, we want the O here to be fully occupied. So P0 1 times B underscore P1. Okay, 1. So P1, and then we want 0.75 times A, and then 0.25 times C. Okay, the answer you submitted, perfectly acceptable, because I believe that on, so no, this is rock salt. So the 2 sites are equivalent. So you could put the O on the one site or the O on the other site. No problem. They're equivalent, so you can do that. So yep, that's the same answer you submitted. Yep, okay, great. So this should work. Okay, we got it. Now for the second one. The second one, I'll just show you. Aflo proto equals 219. So this is why it's important to look at the parent structure first, because we see we have 2 sites. Sorry, we have 4 sites and 2 species. So we're really going to want to use the S for this one. So we're going to plug in the species in alphabetic order. So S, SE, ZN, POC params equals. And we're going to want to have, I'm going to put the zinc on the first site. So P0, 1 times A, no, sorry, 1 times C. Okay. P1, 0.25 times A, 0.25 times 75 times okay. Oh, wait. It did not quite work out. 1 second. 1 times C. Oops. Somewhere I messed up. Oh, S. I'm sorry. We want to use S. I was just advocating we want to use S. And I'm replacing the sites. Okay, let's see. 1 second. So species 1, species 2. There we go. So no P's, we want to use S. Okay. All right. For the third one, I hope some of you were able to try it. It's a little tedious, but the idea is not that difficult. So we want to create for iron copper. We want to span all of these different concentrations with one and different labels with one command. Okay, so Proto can only handle one label at a time. So let's look at BCC. We know that it has one site and 1 species. FCC has it as well. They just have different lattices. Okay, so we're going to put FCC, BCC, and then we're going to put the species. So in alphabetic order. And then POC params equals. Okay, so we want P0 1 times, sorry, 0.1 times. We're going to spend the whole thing. So 1 times A, 0.9 times B. Okay, so this should make just 1. Oh, 1 second. Because I'm running Proto. So with Proto, you can only, because it's spitting out to the command line, we can only do one at a time. So I just want to check that this is right, okay? And then I'm going to change the command from Proto to aflow Proto. Then I'm going to add the BCC. And then just by comma separating, I'm going to create a bunch of different POC params spanning the concentration. So now we'll do 2 and 8. And then we'll do paste 2, 5 and 7, 5. And then we'll do 3, 3, 3, 3 and 6, 6, 7. Paste. Okay, and then we'll go up to 4, 4 and 6, and then 5 and 5. And you could keep going, but you get the idea. Okay, and then we're gonna add generate a flow in only. And that should span these concentrations and for the 2 labels. And you can keep going all the way across the full compositional spectrum. Did anyone have any questions on that? And of course, we can go in and run it and get the number of representative structures. We can very easily do it for the ones that we were playing with in the command line here. Aflow minus HNF cell. Oops. HNF cell. This should give us 27, I think. It's a little big to see with the output. I think the answer was 27. You can just write it to an output file, let it run. Gedit out, and then scroll down, check out all the output. And we get 27 structures. Okay, any questions there? If not, we'll keep going with the lecture, with the talk here. All right, so okay, so we've really, the first part of the of this talk was really focused on generating the structures, okay? And now the idea is that we want to be able to perform, we actually want to get the properties of the disordered material. So we want to perform an ensemble average over the properties of the representative structures. So one example is we can do the ensemble average band gap, okay? So what we do is we calculate we calculate the density of states for all of the structures. And then we calculate the band gaps for all of those structures, and then we ensemble average, okay? So here we have an example of the zinc sulfur selenide system that we were talking about earlier. And this system, as we vary the concentration of selenium, it shows a dependence on the band gap, this optical bowing here, this quadratic relationship in the band gap, okay? And so we see that for a number of experiments, and the blue is what we calculate with aflow, and you can see that the results match very well. It's important to remember that DFT underestimates the band gap, so there's a constant shift in the band gap. Notice that the numbers here don't align directly, okay? So with DFT, we get lower band gap, but the trend is the same as what we expect from experiment. Here we have a magnesium zinc oxide system. We know that for the band gap, as we vary the concentration of magnesium, that the system, the band gap overall increases, and there's a phase transition in the middle. There's a Wurtzite system for zinc oxide, and for magnesium oxide, it's rock salt. And the trend on the band gap changes from linear to sort of a quadratic one here. And you can see that the calculations map very nicely to the experimental values that we see. Okay. We can perform the density of states. So this is, we needed to do this implicitly to get the band gap. But now we can actually plot the band gap, plot the density of states as a function of a particular component and see how the density of states changes. So here for our zinc sulfur selenide system, as we vary the concentration of selenium, we can see that that the band gap here shrinks, and it does so because the conduction band is actually moving closer to the Fermi energy, okay? And it's a little difficult to tell, but the valence band is actually shrinking a little bit too, okay? And for magnesium zinc oxide system, you can really see how the change happens here. The conduction band gets pushed further and further back. And so the band gap really increases as we increase the concentration of magnesium in the system. We can also do magnetic properties, although this is a little difficult with DFT, but we tested for the copper iron system. As we vary the concentration of copper, we know that iron is magnetized, copper is not, so the magnetic moment for the material drops off. And even through a phase transition, this trend is mostly linear. And so we see that our calculations reproduce these results very well. And you can even look at the density of states. And so we know that from a density of states perspective, as the system becomes less magnetized, the density of states at the Fermi level, the difference between spin up and spin down should approach zero, right? And so we looked at these results, the density of states near the Fermi energy, and you can see that the density of states decreases as you increase the copper concentration. Okay, so an important test for this model is that we want to make sure. We want to make sure that with the model that, okay, we've been relying on the fact that we want to use the smallest supercell that accommodates the stoichiometry exactly. But there's no restriction on that. We can actually go beyond that. We can actually model the system with an even bigger supercell. So we're going to have a bigger supercell, and we're going to have more supercells representing that disordered system. So we want to make sure that as we increase the supercell size, as we increase the HNF size value, that the accuracy gets better. That would be a good indication that the model's working. And so here we looked at the band gap as we go from the stoichiometry that matches we go from the HNF value that matches the stoichiometry exactly to one that is larger. And so you can see that the supercell size is increasing, and you see that the error with respect to, this is error, by the way, I'm missing the y-axis. You can see that the error with respect to experiment decreases. Okay, so this is a good indication the model's working. We can also look at the magnetic moment. And so you can see here that the calculations, some of them deviate a little bit away from experiment. So we took this section here and we modeled it with supercell sizes that were larger than what was needed. And you can see here that with the magenta or the pink here, that the values much better model what we see in experiment. Okay, so what about thermodynamic properties? So what we can do here is we can look at the mixing enthalpies for these systems. Okay, so the mixing enthalpy is just the energies of the structures. So we take those energies and we subtract off the input structure. So in this case, we have pure zinc, sulfur, and here we have pure zinc selenium. And so we take the energies of the atoms the energies of the structures, the supercells, and we subtract off the stoichiometric weighted endpoints. Okay. And so we can look at these enthalpies of these mixing enthalpies, and you can see that. So as we go from left to right, there's a lot of data here, but I want you to focus on is that as we go from left to right, the system becomes more and more difficult to synthesize. Okay, so this system here, this concaugenide system, we know that we can actually synthesize the disordered material all throughout the full range of selenium concentration. The magnesium zinc oxide system forms a solid solution phase up until about the orange here. In the red region, we actually see phase separation. Okay. And in the iron copper system, most of the region is difficult to form. Okay, so there's definitely a phase separation right here along this red, but the orange where some methods have trouble synthesizing this concentration, that spans the full range of concentrations. So all I want you to notice here is that if we look at the mixing enthalpies, the mixing enthalpies are pretty small for this first system. They get larger for the middle system, and then for the last system, they're very large. And so what we expect is that the entropy of the system, there needs to be more entropy to accommodate for this positive enthalpy, this mixing enthalpy. And so this system here is easier to form, and this system here is not easy, is very difficult to form. So we can see that reflective in the mixing enthalpies. What about parameterizing the entropy? So we talked about these two types of disorders in the beginning. We have glass, and we have glass, which is structural disorder, and chemical disorder here. If you take this sort of disorder to the extreme, as I said, we get glass here. And what we get for chemical disorders, we get high entropy systems. Okay, so we've come up with descriptors for quantifying whether a system is likely to form a glass or a high entropy alloy. Okay, so respective descriptors are called glass forming ability and entropy forming ability. So we looked at a known metallic glass system, copper zirconium system. And we're going well on time. A known metallic glass, and what we did is we looked at this. Remember, this is the convex hull, so this is the formation, the enthalpy of formation, and then this is the full range of compositions spanning from copper to zirconium. We looked at the 50-50 concentration, and you can see here that there's a very tight cluster of structures, of different structures, that they have very similar energies, but they're very different structurally. Okay, and we can quantify that. We can actually do this analysis more rigorously with what's called the thermodynamic density of states. So we look at, along a particular concentration, a number of different structures per slice of energy. Okay, and so if this density of states, this thermodynamic density of states, is very wide, then that means that all of these different structures have very different energies. But if it's very narrow, you can imagine that there's a lot of confusion in the system about which structure to choose. Okay, so this is the idea. We're looking for a narrow concentration because this quantifies disorder. This quantifies confusion in the system. So we use this descriptor to quantify whether a system was likely to form a metallic glass. So if if this distribution is very tight, there's a lot of confusion during nucleation. And it's going to have a difficult time picking which structure to form. Okay, and so the analogy I use is that imagine that you are going to the ice cream store, and you find that you find that there's only two flavors, vanilla and chocolate. Well, if you're a chocolate lover, you know which flavor to pick. It's an obvious choice. Let's say you go next door to the next ice cream shop, and there's 50 different flavors, 25 are variants of chocolate. Well, which variant are you going to choose? The answer is you might come out of the store with more than one ice cream flavor. Okay, and so that's the idea here. So during nucleation, it has trouble picking one of these crystalline formations, and so it picks kind of a mixture of all of them, which is a glass. A glass has a structural disorder. So if we limit ourselves, if we, when we're defining this descriptor, if we allow the structure, if we allow the lattice to be any variant it wants to, whether it's BCC, FCC, hexagonal, if we analyze all of the different possible arrangements of atoms on lattices, then we have a glass forming ability. However, if we restrict our lattice to one type, such as what we've been doing for the for constructing Pox structures, where we've been looking at derivative structures from a particular focused fixed lattice, then that concept is going to be called the entropy forming ability. Okay, so we use this entropy forming ability in a study of metal carbides. And we looked at, we were looking at these 56 different combinations that we created from the 8 refractory metals that I told you about. We actually formed the affluins, remember, in the demonstration. So among these systems, we actually calculated the respective entropy forming ability. And those that had the highest EFAs, we were actually able to create these materials. We were actually able to synthesize them. Okay, so these are high entropy materials. Here are the compositions. And here are some of the experimental data. So you can see that it's fairly homogeneous from this micrograph here. And you can even see from the this is the distribution of different elements, that the distribution is fairly random and it's evenly distributed. It's not like we have clumps here, holes there. It's very well distributed. This defines well this high entropy material. So how do we quantify the entropy forming ability? Well, we look at these Pox structures. So we create the Pox structures and we create all 49 derivative structures for all of these 56 combinations, right? That's like 2,000 different structures. And we look at the distribution of energies for all 49 of these structures, right? And we look at basically the entropy forming ability is the standard deviation of this distribution. Well, it's the inverse of the standard deviation. So you can see here for this system that has a high EFA, that the standard deviation is very small, and that means that it's going to have a very large EFA. It's got the highest one, 125. And as sigma, as the standard deviation increases, the EFA decreases, and that quantifies a system that we expect is going to phase separate, not form a solid solution, a high entropy system. Okay. So what does this EFA really mean from an experimental perspective? We have this Bragg's relationship here that comes from experiment. Okay, so as we analyze the XRD spectrum, this equation is very well known from experimenters. I want to focus here on this epsilon. This epsilon quantifies the chemical inhomogeneity in the system. It's associated with the broadening of these peaks. Okay. And so you can see that we've plotted epsilon versus the inverse of the EFA, and we get a very nice correlation. So what does this tell us? This tells us that the systems that have the highest EFA are expected to be the most chemically homogeneous as well. So here we have our high EFA system, and it has the lowest epsilon, and it's got the highest EFA, which is the lowest inverse EFA. Let's focus in on this system. The system's of particular interest because in a lot of ways it defies intuition. So the high entropy carbides all have a rock salt structure. Okay, so this is the structure that we've been using in creating all of our systems. So let's look at some of the other high entropy carbides that we discovered and synthesized. So we have hafnium, niobium, tantalum, titanium, vanadium, and carbon. Okay, so if we look at the precursors, so the way we make these high entropy systems is that we mix together metal carbides. So we mix together hafnium carbide, that's a precursor, niobium carbide, and so on and so forth. All of these precursors in this system to make this high entropy alloy has a rock salt structure. The same cannot be said for this molybdenum structure. Okay, so it has some non-rock salt precursors. It has this alpha phase, which is molybdenum 2 carbon, right? And this is actually a little strange because it doesn't have the rights to balance the stoichiometry. It's going to be a little difficult because now we have MO2C. We don't have single metal, single carbon. Same for the for tungsten. We have hexagonal alpha, this alpha phase, which is W2 C. Okay, so there's something not intuitive there. If you asked an experimentalist if you expected this to form a solid solution, they might tell you no, just on the basis of the fact that there's non-rock cell precursors. Interestingly enough, this system is very, very high above the convex hull. Okay, so if you look at the 6-dimensional convex hull, and you were to do this analysis, you would see that this system is 150 MeV per atom above the 6D hull. That's way higher than that 25 MeV cutoff that I talked about for room temperature excitation. So the system has to have a lot of entropy to overcome that penalty from enthalpy. And it has the highest CFA, which means that it's also the most homogeneous. So there's a lot of different reasons why this system is very interesting, kind of defies intuition there. Here we have a plot of the hardness values. All I want to point out is that you can look at the hardness values of the precursors and take an average. This is called the rule of mixtures. And what we see consistently is that a lot of these high entropy systems have even higher hardness than the average of all of their precursors. So that means that in forming a new system where the mixtures all together, we get even higher hardness. This is a property that is very exciting for this community because achieving this higher hardness, and in some cases it's even 50% higher hardness for some systems. This is a big benefit for these systems, for these materials. Okay, how are we doing on time? Very good. All right, so I'm gonna share my screen. You guys can still see my full screen here, right? Give me a thumbs up if you do. Good. Okay, great. So we're going to do the last exercise. We're not going to break up into breakup rooms because this one's a little simple, but it takes a bit of time. So go to, we'll actually do this together. So let's go back and we're going to go into 2 post-processing. And from here, we're going to go inside of this. So this is the special system I was talking about, this molybdenum system. So this is the run for that system. We're going to go inside this one. We're going to go inside. So that was the chemical layer of pseudopotentials. Then there's the structural layer. So we're going to go inside that layer. And now we have, okay, so this is our, we created the A-flow in, we've created all the A runs. And inside of the A runs, we have all of the VASP data we need in order to process the data we're looking for. Okay, so just like every other module, you just do A-flow minus run. And this is going to take a bit of time. So I will take some questions if you guys have it, because basically what it needs to do is it needs to go through each directory and analyze. Basically what's happening is that it's trying to determine properties for a range of different POC temperatures. Remember, there's that T parameter. So we're going to vary the temperatures and we're going to see what the properties look like over a span of different temperatures. And while this runs, I'll take questions. But I'm also going to. How do I get out of full screen? Okay. Yeah, if anyone has questions, feel free to post it on the chat or unmute yourself. I'm going to open up another terminal because I want you to see what's inside these files as they're writing. A4, 12. Okay, so one of the files, well, first, let's take a look. One of the things I did not show you in the A-flow in. Okay, so do we have? No, we don't. There's an additional parameter you can set if you don't want the default values, but inside of the A-flow RC, you can just follow my screen here, and I'm going to make the terminal larger. Okay. All right, so what the temperatures that it's going to run by default, if you don't feed in another parameter, is that it's going to go from 0 temperature to 2,400 Kelvin, and it's going to go in increments of 300. Okay, so that's what's going on right now. And you can see that one of the files that it's writing out, the new file that it's writing out, is this aflowpoc.out. So let's take a look at the file. It's still writing to it, but there's some results that we can look at. So inside of this output file, we get a lot of different properties from the analysis. We first get the degeneracy for every supercell. Okay, and so there's 49 different supercells. They all have 10 except for the last one. The last one has 120 different structures that are equivalent to it. So it has a degeneracy of 120. So we have the degeneracy values written there. We also have the enthalpy of every supercell as it's been calculated. So this is that DFT energy that we get. So all those values are written here. And it points out which one is the ground state. So which one is the minimum energy. Okay, so it writes out ground here. It performs an ensemble average to get the average enthalpy. The average enthalpy here, it's enthalpy mix per atom. So that's that value here. And then we get the entropy forming ability. So see here, based on, it depends on the particular, on how, which machine you run on. Sometimes VAST gives you slightly different energies, but basically we get the same values we got before. We get 117 here. I think I showed earlier it was 125, but 117 is basically what we got earlier. Okay, so now at 0 temperature, we get the probabilities of all the structures, and you can see here that as I was telling you before, so at 0 temperature, the probabilities of all the supercells except one is going to be 0, except for the ground state. And so that was supercell 27. That one has a probability of 1. So when we do our ensemble average properties, basically the disordered system is going to be that of that supercell 27. Okay, but as we increase the temperature, the probabilities of the other supercells start to increase. Okay, so at 300, we see that supercell 27 still has a large probability here, roughly 27%, but or probably about a 0.27. It says out of 1, and the others are going to have much smaller probabilities. Okay, so you get these properties for all of these different temperatures. It should still be running. Another thing you'll see is that as it calculates the properties at each temperature, it's also going to write out a DOSCAR, which is the file we need to plot the density of states at each temperature. Okay, so we get one for 0, 300, 600, 900, so on and so forth. Okay, so we look inside.
I think you have a question in the chat.
Oh, great. How is a supercell property computed? It depends on the property. The point is that this is a particular, do you mean the probability or do you mean a specific property? I think you meant probability, right? Okay, probability. Great question. So the probability, if you recall, we had this equation earlier. This. Okay, so the probability for each supercell is quantified by the degeneracy multiplied by this exponential term. Okay, and so this exponential term is the enthalpy of that particular supercell minus that of the ground state structure divided by Boltzmann constant times this temperature parameter. So that's how that probability is defined. So, and then then you divide it by the sum here, which makes the probability out of 1. Okay. Great. If I want to use xtol instead of UFF to generate, what modification do I need to do? So what I recommend doing, there is actually a way of doing it with the code, but the best way to do it is if you want to see what structures are unique. Okay, so you're going to want to take this file, so aflowpoc structures all.out. And I'm actually, if David's there, I'm going to ask that he gets the command ready because I don't know the command off the top of my head. But this file contains all 600 structures that all 600 different permutations and different supercell sizes that you can get. And you can actually take this file and you can run it in with the Xtel Finder command. David, do you have the command?
Yeah, so it's aflow compare materials underscore materials space minus F, capital F.
Can I do it with an Excel file?
Yes, yeah, equals, and then that, and I would recommend do ignore symmetry, otherwise it'll take a long time.
Okay. So no symmetry is what? Minus no symmetry?
Minus ignore underscore symmetry. Yep, so if you do that, then it should hopefully work. Yeah, so the longest part is going to be because it has to load all 600 structures.
Right.
But it should take like maybe a minute.
Yep.
And then again, yeah, if it's taking too long at some point, you can do minus NP equals however many processors, but it should be a minute. Thanks for typing it in the chat, Marco.
What the answer should be 54, right?
Correct.
Okay. So you see, you get a little more than what you had before. So 49 is what we calculate. So probably that one supercell that had 120 structures in it should really become 3 or 4, whatever it is. Will it also give the degeneracies? That's a good question.
It'll tell you which ones match. So then at that point, you have the counts of how many match to this structure, this unique structure. So
There we go. Yep, there you go. So you see that.
yep, so there you go.
And it tells you which one. So it took the name from the file. So, 471 out of 600. So here you can see which ones, gives you the full analysis. So we get 54. Awesome. Glad to hear. Okay, so awesome. So that's one party trick. The last one is plotting the density of states. You can do it with our simple. We've already run this command before during my session, actually. Plot DOS should work. I don't know if you need the equal sign. And while that's running, I'm going to open up the page 4. Okay. And we get all these very nice plots here. Okay, so this is at 0 temperature. We get the plots for, okay, so this is broken up by SPD, F, if we have it. You can also do plot DOS, and then I think it's projection equals species, if I remember correctly. Seems to be working. Let's see. Yes, there we go. So this one was broken up by SPDF, but you can also get the projection as a function of the species. And I'm trying to find, we don't get the full label, DOS orbitals. DOS orbitals. One of them's going to say species. So this breakup is by the contributions for each species. Okay. And so we get the full set. So I have a nice little GIF here for not GIF as in pictures. Let's see. Slide. So you can actually analyze how it changes with as a function of temperature. Doesn't change very much here. Okay, so the density of states is pretty much once you go from 0 to, because remember at 0 we have just the density of states of the ground state structure. And then you get this kind of broadening or this averaging out property of the density of states because we're averaging over different supercells. Okay. And then you can also look at it as a function of the species. All right. So that wraps up my discussion here. Yeah, that we've already gone through that. That wraps up my discussion here. Does anyone have any questions? If not, I will wrap up the session by saying thank you very much. I'll take questions later if you have them, or you feel free to email me. I'll put my email in the chat if you have any questions about disordered materials. Thank you very much, and appreciate your time.